Good evening, everyone. Welcome to week 7 lecture. We are week 7, where we'll discuss some of the topics regarding the solution. So, we'll start with some problem. Question number 1. The average the average number of solute solvent pairs in lattice model can be approximated as, there are four options: in total z phi square, b in total into z phi into 1 minus phi, c in total, this half there, this option is z phi 1 minus phi, d half into in total z phi square. So in this problem, the in total is basically denoting the total number of solute particle and solvent particles. Phi is the volume fraction of solute particles, 1 minus phi is solvent particle volume fraction, and Z is the coordination number of the solute particles or solvent particles. Now we have to revisit the ideas of lattice model to actually answer this question. So we'll start from the very basic of lattice model, construction of the lattice model, and we slowly build up from there. Now in the lattice model, which is a toy model, approximated model, lattice model is basically a toy model to represent a solution. One of the so the construction of this lattice model is something like this. We construct a lattice like this, where there are cells of equal volume like this, and these cells are either filled with solute or solvent like this. Randomly I am putting some solute and then some solvent, something like this, randomly. There is no preferred choice here. So, and the volume occupied by the solute and solvent, both of them are equal. So the V solute equal to V solvent equal to Vc. Now what will be phi solute? The volume fraction of the solute particle. So in P, Vc, which P is the P denotes the solute and S denotes the solvent. So in PVC, total volume occupied by the solute molecules by NP into Vc plus Ns into Vc. This is basically NP plus Ns is the total number of N total basically, and so basically this is the denominator is the total volume of this cell, all the cells together with, and upper is the only volume occupied by the solute molecules. So it is volume fraction of solute. So if I take Vc common, this will become On the other hand, if I calculate phi solvent, this will become Ns by Np plus Ns, which is basically 1 minus phi solute. So this is the volume fraction. Now to write down the actual Hamiltonian for the system, we need to write down the free energy uh, from the Hamiltonian, and to construct the free energy we need two terms. One is internal energy altogether and another one is the entropy term. Both of them we need in this case. So we consider there are interaction energy between solute interaction, solute which we call epsilon pp, solute solvent interaction which we call epsilon ss, and solute solvent interaction which we call epsilon ps. These are the three types of interaction. These are the all interaction present in the system. Now then total energy clearly will be uh, total energy of the system will be epsilon pp into npp, number of solute pairs, plus epsilon ss in ss, number of solvent pairs, epsilon ps in ps. Now if I want to calculate all of these in pp will be, now let us go back to the diagram again. So suppose there are z neighbors of each solute and each solvent. Suppose it is a 2D lattice kind of structure here. So clearly in this kind of representation z is 4 if all the particles are surrounded by same kind of particle. Suppose z is the coordination number, then number of pairs will be given by phi into z of phi into n total, which is np plus ns into half. The half come because I am counting. So first I am counting, suppose one of the solute particle and how many neighbors it can have. Then again I am counting its neighbor. Then also I am counting the same interaction pair. So to avoid double counting of the same interaction pair, we introduce a half in this. Similarly, in SS, this is also will be 1 minus phi. This is the volume fraction by the solvent molecules. Z coordination number into 1 minus phi into n total, and again there will be double counting. But when NP is considered, there no double counting, because we are counting either protein, either P or either S. So we'll count from P side how many PS pair are there, or we will count from S side how many PS pair are there. So there is no double counting. Phi z into 1 minus phi into n total. So our question was how many solute solvent, that means PS pairs are there. So that comes out to be z into phi into 1 minus phi into n total. Z into this option, z into phi into 1 minus phi. Phi is the supposed volume fraction of solute. Then it will have on an average z neighbors. Volume fraction of the solvent is 1 minus phi. Total number is n total, np plus ns. Correct. So this was, we have already done. Then how many pairs are there, we have found out. Now the job is to write down the energy explicitly. So, and our next question is related to that only, that. So we'll come to the next question in a moment, but let us neatly write down the full energy term. So as we have defined, the energy will be EPP into MPP, ESS into NSS plus EPS into NPS. So our job is to multiply only that, and then we will only keep, so E will be something like in total into Z by 2 phi square epsilon pp plus 1 minus phi whole square epsilon is plus 2 into phi into 1 minus phi epsilon ps. Now in the free energy, only double derivative of the free energy matters. Double derivative of the free energy with respect to phi matters. So for that reason, we will only keep the phi square or a higher order term in this expression. So half in total into Z epsilon pp phi square plus epsilon ss phi square minus 2 epsilon ps phi square. We'll take phi square outside. In total, Z phi square by 2 into delta epsilon. We call this whole term as delta epsilon, which is, so delta epsilon is given by epsilon pp plus epsilon ss minus epsilon ps, right? So the whole term is given. So this is called, delta epsilon is called effective interaction. Clear? Effective interaction. And okay, so we got energy. Now our job is to calculate what is the entropy term, because we want to write down free energy, which is E minus Ts. So we got epsilon in terms of epsilon, the energy. Now we have to calculate what is entropy. To calculate entropy, first we need to understand how many number of configuration is there. So in this picture, in the lattice model picture, suppose there are all together in total number of solute and solvent molecules together. Now Np is the number of solute, Ns is the number of solvent. So total is Np plus Ns. Now, so according to the formula of permutation and combination, number of ways I can arrange this Np and Ns is given by Np plus Ns factorial by Ns factorial Np factorial. This is fairly simple formula, I guess, for you. And this entropy will be then ln omega, proportional to ln omega, and that is, will do log of this Np plus Ns factorial minus log of Ns factorial minus log of Np factorial. Then we will use the Stirling approximation, and after doing everything, we'll get the result as minus in total phi ln phi plus 1 minus phi ln 1 minus phi. This is the log of omega. So if we now multiply it with kV, that will give us the entropy. So we are all set to write down our full free energy. So, but before going to the full energy, let us discuss one question from sample assignment. Question number 2. In the lattice model, the number of ways of placing in p molecules in total cells, in total is Np plus Ns, uh, is given by so there are options. W is equal to Np minus Ns factorial by Np factorial Ns factorial. Option B, Np plus Ns factorial by Np factorial Ns factorial. Option C, W is equal to this is Np factorial Ns factorial by Np plus Ns factorial. Option D, Np factorial Ns factorial by Np minus Ns factorial. So clearly, as we have discussed, the total number of possibilities will be Np plus Ns, which is the total number of cells in total, and divided by Np minus factorial by Ns factorial. So this is the correct option, option B. Okay, let us come back to our free energy writing. So free energy is given by the formula E minus Ts. We have explicitly found out the form of E and S. So we can write down what is the free energy. Rather, we are interested in free energy density, which is free energy by volume. It will be kBT. Let me write down one more step here. If by in total into Vc. In total is Np plus Ns, and there Vc is the volume associated with each of the cell. So this is one of the assumption of the lattice model, that we consider in lattice model, solute or solvent, whatever it is, it always occupies same amount of volume, which is given by Vc. So total volume will be in total into Vc. So this will be kBT by Vc phi ln phi plus, I am writing down the contribution from entropy, ln1 minus phi minus chi phi square. Now I have not defined chi before, but chi is basically negative of this whole quantity. So this you can write minus chi phi square. Then chi will be the negative of in total z by 2 into delta epsilon. So this is our free energy density. And now, as we have already discussed, that in the free energy density we are only interested in terms which are of the order of phi square or greater, because we are only interested in f double derivative. So only if the order of the power of phi is greater than 2, then only it will survive in the double derivative. So here we are going to do a trick. We will add one term here which is chi phi. It doesn't matter in the free energy because it is a first order term. We are interested in double derivative, so we are adding this extra term which will make the expression of free energy density a little bit more symmetric. So phi ln phi 1 minus phi ln 1 minus phi plus chi of phi into 1 minus phi. So just introducing one extra term which is not directly affecting the free energy, but it is making the whole expression a little bit more symmetric. So this is our total free energy density for the solution. If I explicitly discuss the contribution of each term, this is basically entropy of solutes. This is entropy of solvents, and this part interaction energy, uh, which you can say effective interaction energy, because we have dropped many terms, only kept some of the terms, so this is effective interaction energy. So this part, the first two term is the entropy contribution, the last term is the internal energy contribution. Altogether this is the final expression for the free energy. Okay, let us do one more question then from our question bank. Question number 3, the Helmholtz free energy. Basically it gives all possible option and it asks what is the Helmholtz free energy density as a function of phi. Question number 3 is f of phi is what? So we have discussed already, derived the whole expression. F of phi is kBt by Vc phi ln phi 1 minus phi ln 1 minus phi plus chi phi into 1 minus phi. Now in this case you can write chi as explicitly as half into so there is a little bit problem here. So we have defined chi as, so explicit expression for chi is in total z delta epsilon by 2 with a negative sign. This is our expression for the chi, right? No issues. So in this case we are taking a kBt outside, so altogether it will be, because kBt is outside, this will be half z delta epsilon chi square. all good. Yeah. Now, any question here? Now, if we have the free density term, from that, what we can do is we can calculate what is if first derivative f prime of phi, f double prime of phi, and f triple prime of phi. These three quantity we should calculate. So using these quantities we can get properties of the solution. So let us first take the question we want to answer from this part, that first of all let us take this question. Question number 4. Lattice model finds the dash, fill in the blanks type question, Hamiltonian for a polynomial solution. Now, because this is a lattice model is altogether a so there are options like exact, option B approximate, C relative, D absolute. So so while building this idea of lattice model to describe the solution system of solution, uh, we have made a good number of assumptions. So this Hamiltonian is not exact, but it is approximate. So there are multiple assumptions that solute and solvent molecules occupies equal amount of volume, which is denoted by Vc, which is one assumption. There is another assumption that there is always Z is a coordination number. Z neighbors are always there, which may not be equal in all possible scenarios. And also we have dropped some of the terms in the interaction energy and while writing the entropy also. So altogether the model we are building here, lattice model, this captures some of the properties of the solution, but it is not a exact approach. This gives some rough idea about the thermodynamics of the solution. The next question is this question we'll discuss now in detail. Coexistence curve is also known as option A binodal, B spinodal, C bimodal, D critical line. So first we have to understand what is binodal and what is spinodal. So let us go there slowly. So we got the free energy density formula. From that, what we can calculate is the first derivative of the free energy. So F prime of phi, which is del phi of F, and if we equate this to 0, we get something like chi b into 1 minus 2. So this calculates chi b 1 minus 2b plus ln of phi by 1 minus phi, which is 0. From this we get equation of chi b, which is minus 1 by 1 minus 2b ln of phi by 1 minus phi. So this is one equation. Then we can calculate f double prime, which is del 2 f del phi 2, which is kbt by vc 1 minus 5 plus 1 minus 5 to chi. So from these we can calculate what is chi is. That is half by 5 plus 1 minus 5. This is exactly symmetric about phi is equal to half. If we equate f double prime equal to 0, this will give chi is this. And from if triple prime equal to 0, equating these, we will get the phi c, which is half. So first derivative gives us the equation of chi b, which gives the bimodal line, and then double derivative gives us the chi s, which is equation of the So if we want to calculate what is the critical chi, we have to put in the chi s phi is equal to phi c is equal to half, which will give half into 2 plus 2, which is 2. So critical chi, which is critical chi. Now if we plot chi versus phi, we get a symmetric line about half. So this point is phi c is equal to half, and there will be another line here. So this line is called the binodal, which is given by chi b phi. This line is called sphenoidal. This particular point is chi c because it is chi s derived at phi c is equal to half. Now what are this region called? So there is a in between region like this. This region is called metastable region. The region below it is stable and above is unstable. So this region is unstable and this region is metastable. These are metastable region. So if chi is less than chi c, there is no phase separation, and if chi is greater than chi c, certainly phase separation. So this line binodal line, this is also restricting the phase separation and not phase separation. So on this line there is a coexisting scenario. So the line of coexistence is also known as the binodal curve. Okay, line of coexistence is also known as bimodal. Now this all of this discussion, whatever we have done, it is for a solution where solute and solvent both of them are particles. Now if we want to calculate these same properties for a polymer system, in that scenario the solute, which is itself a polymer, the solute particles are joined together. So only one difference will be there in the whole free energy, is that the solute entropy will decrease because there are not that much freedom left. So let so if we want to write down, say, lattice model of polymer system or polymer solution. So in that case, if we draw this kind of a lattice and there are cells like this, suppose. Now there are solvent molecules here and there. Along with that, there is a polymer, but this polymer is joined like this. So there will be not as much entropy as before if this all the polymer, these beads are separate and they can randomly take position anywhere in the whole lattice. But that is not the case scenario because they are joined together, so entropy will decrease by a factor of n. So f of phi t now will change like kBt by Vc. Everything will remain same, but the contribution from the solute phi ln phi will be divided by n. N is the number of molecule in the polymer, or in our old language this is NP. So this will be 1 by other things will remain as it is, plus chi of phi into 1 minus phi. So this is fine, but the only problem here is that previously the whole expression of this free energy was symmetric about phi is equal to half. So if you replace phi by 1 minus phi, there will be no change. But due to the introduction of this quantity 1 by n in the whole free energy term, now the problem will be uh, this is no longer symmetric about phi is equal to half. So if you replace phi by 1 minus phi, the expression is no longer similar. So in this case, if we want to calculate the same kind of chi versus phi diagram, so this is also calculated in the lecture, you can see. So similar way we have to calculate f prime, f double prime and f triple prime, and from that we will get all the quantity of our interest. So chi is will be half into 1 by phi n plus 1 by 1 minus phi from phi c, which was earlier half, now it has changed to 1 by 1 plus root n, and chi c critical, that we will get putting phi c in this above expression, half into 1 by n into 1 plus root n plus 1 plus root n by root n. Now if we take approximation that n tends to very large number or infinity, in that case we get back chi roughly equal to chi c is equal to roughly half, because the first term will go to 0 because 1 by n sitting is here, but this is of the order of same, so we can approximate the second term as 1. So second term we can approximate in the large n limit as 1, this goes to 0, so altogether chi c tends to half. So yeah, so in this case the chi versus phi plot, chi versus phi, it will be as non-symmetric curve, something like this, something like this, yeah. And there will be a metastable region in between sphenoidal and binodal. So this is binodal, this is sphenoidal, and this region is metastable, this is unstable. So phase separation is possible only above, phase separation possible here, no phase separation here. Okay, and this particular point will be phi c, and associated chi will be chi c. Chi c is half and phi c is 1 by 1 plus root over n. Now suppose we are dealing with the solution of a polymer. So chi c is half is the critical. So if chi c less than half, what happens? Chi c greater than half, what happens? So chi c half is critical. So think about chi c less than half. In that case, no phase separation is there. So no phase separation in case of polymer scenario, what does that mean? So polymer is completely mixed in the solution. It is spread out. It is not a collapsed structure anymore. So phi c less than half is like a good solvent. Just think about our discussion on self-avoiding work, and chi c greater than half is bad solvent. So in that case, phase separation is happening. So the polymer is coming in a collapsed conformation, and it is becoming a small uh, structure, collapsed structure, because it is not mixing properly with the solution. So it is phase separated from the solvent molecules. Solvent molecules are separate, and this polymer is a collapsed structure, making a blob kind of structure. So that is the property of a globule, compact globule, which happens only if we put polymer in a bad solvent. Now in between these, chi c is equal to half is basically the theta solvent. So these we have understood from the point of view of, so suppose this is SAW, sorry, this is SAW, this is globule, this is random. So what was, so there is a question related to this. So the question is, so this is matching type question. So basically chi less than 0.5, chi greater than 0.5, chi equal to 0.5, a bad solvent, b theta solvent, C good solvent. So you have to just match which condition matches what to what. So chi less than half is certainly the good solvent. So this is 1, 2, 3. So 1 goes with C, 2 goes with greater than, so poor solvent, bad solvent, 2 goes with A, and 3 obviously goes with. So this was the question. Now, so here we have discussed in detail the solution of solvent and solute, and solution of polymer, where solute particles is itself a polymer connected with a polymer chain. Now in this whole concept, there are multiple thermodynamic formula used, different parts. So there is 2-3 questions from the thermodynamics itself. So quickly, these are all known from your thermodynamics knowledge, I guess. So what is the Helmholtz free energy formula? Helmholtz, this is question number 7. Helmholtz Helmholtz free energy formula. So F is minus kBT ln Z. This is the formula. Then how can we write down the partition function? Partition function. So Z is partition function here. So there is question like how can we write down Z? Z is sum over all possible configuration exponential of minus beta epsilon I, ith configuration. So this is the part. So I can give you small example, like if there are two energy E1 and E2, the Z will be basically e to the power minus beta E1 plus e to the power minus beta E2, something like this. Now if you take minus kBT ln of Z, that will give you the free energy. If you want to calculate average energy, you can calculate from this. If you want to calculate something else, like some other formula, average energy or average square of energy, all these can be standard deviation, all these can be calculated from this partition function. Yeah, so what else, thermodynamics question, one more question is there. How can we write down? Question number 9, right? Yeah, question number 9. How can we write down G, which is function of Np, Ns, T, P? So G is gives free energy. This is function of NPT always. So here two type of energy is there, because P is solute, S is solvent, and this will be dependent on the formula is E plus PV minus TS. Now this can be written E minus TS is F. So E minus TS is F. So this can be written as F plus PV. Now if this is an incompressible fluid, then volume is no longer a variable. F is in general is a function of mv and T, but if it is incompressible, the volume is not changing anymore. So if in T, N is two type, so in P N is T plus P. So how these formulas are derived? These are derived using or transformation called Legendre transformation. So for each type of variable, so for suppose G is like NTP, there is F which is defined as NVT. So this kind of all different kind sets of variable, there is one uh, thermodynamic potential is defined, gives free energy, Helmholtz free energy, uh, then enthalpy and internal energy. All these are well defined in different for different variable sets. So all these are connected by some formula. So there are multiple formulas like this. So also like G is H minus Ts, H is E plus Pv. So all these formulas are there. So you can consult any of the standard thermodynamics book to understand this formula. Okay, any doubt? Okay, if not, let us stop today here. We'll see you next week. Thank you.